Hello, science fans! Today we're diving into something that's all around us, even if you don't see it. It's called non-sterile filtration. Now, what does that mean? Let's break it down. Filtration is just a fancy word for cleaning a liquid or a gas by passing it through a special material that catches unwanted stuff, like dirt, dust, or other tiny particles. Think of it like making coffee. You pour hot water over coffee grounds, but a paper filter stops the grounds from getting into your cup. You get the delicious coffee, but the yucky grounds stay behind. That's filtration in action. It's a physical process of separation. So, what about the non-sterile part? That sounds important, and it is. In some places like hospitals or labs making medicines that go directly into your body, everything has to be perfectly, absolutely 100% clean of all living germs. That's called sterile filtration. But for many, many other jobs, you don't need that level of clean. You just need to get the solid gunk out. Non-sterile filtration is all about making things cleaner, clearer, and safer for machines and products, without the extra, super intense step of killing every single microbe. It's the workhorse of the industrial world, quietly making things better everywhere. The main idea here is to remove solid particles from a fluid, which could be a liquid like water or a gas like air. These particles could be anything from tiny bits of sand in your drinking water to specks of rust in a chemical mixture. By trapping these particles, we can purify the fluid, protect sensitive equipment from getting damaged, and make sure the final product is just right. It's not about creating a germ-free environment, but about achieving a specific level of cleanliness that is good enough for the job at hand. This makes processes more efficient and reliable. Consider this. You wouldn't use a hospital-grade surgical mask just to keep dust out of your mouth while you're cleaning the garage, right? A simpler dust mask does the job just fine. Non-sterile filtration follows the same logic. It provides the necessary level of particle removal for countless applications in manufacturing, water treatment, and food and beverage production. It is a fundamental tool that helps industries run smoothly, safely, and economically, ensuring that the products we use every day meet the quality standards we expect, all without the extreme requirements of sterility. So why do we go to all this trouble? What are the big goals of non-sterile filtration? Well, the first and most obvious reason is to make things cleaner. We want to remove visible and invisible particles from a liquid or gas to improve its quality. Think about the water that comes out of your tap. It started as river or lake water, full of sediment, algae, and other floaties. Water treatment plants use massive filtration systems to trap all that stuff, giving us clear, clean water to drink. This purification is crucial not just for water, but for making chemicals, drinks, and many other products. Another huge goal is protecting our precious equipment. Machines in factories can be very expensive and very sensitive. Imagine tiny, gritty particles of sand or metal shavings flowing through the delicate pipes and pumps of a manufacturing plant. These particles act like tiny sandpaper, grinding away at the machinery over time. This can cause equipment to break down, leading to costly repairs and stopping production. By putting a filter upstream, we catch these damaging particles before they can cause any harm. It's like putting a screen on your window to keep bugs out of your house. The filter is a shield for the machinery. Filtration also helps make industrial processes more efficient. When you have a lot of unwanted gunk in your system, things can get clogged up, slowing everything down. It's like a traffic jam on a highway. By removing these particles, we ensure that liquids and gases can flow smoothly and quickly, keeping the production line moving at top speed. A clean system is a fast system. This means factories can make more products in less time, which is good for business and helps keep the costs of a product down for all of us. It's all about creating a smooth, uninterrupted flow. Finally, filtration helps companies meet rules and regulations. Many industries have standards they must follow to ensure the safety and quality of their products. For instance, the food and beverage industry has strict rules about how clean their ingredients must be. Filtration is a key step in meeting these requirements. It provides a reliable way to control the number of particles in a product, ensuring it is safe for consumers and meets the legal standards. So, filtration isn't just about making things look nice, it's about safety, efficiency, and following the rules. It's a critical part of modern manufacturing. Non-sterile filtration is a true superstar, working behind the scenes in more places than you might imagine. Let's take a tour of some of its most common workplaces. One of the biggest is municipal water treatment. The water you use every day for drinking, cooking, and bathing has been through an extensive filtration process. Large-scale filters, often made of layers of sand, gravel, and charcoal, remove sediment, organic matter, and other impurities from river or reservoir water. This is the first major step in making water safe and palatable for an entire city, proving that non-sterile filtration is a cornerstone of public health and infrastructure. The chemical manufacturing industry is another huge user. When making everything from plastics to paints to fertilizers, companies mix various liquid chemicals. These liquids often contain undissolved particles or byproducts from chemical reactions that need to be removed. Filtration ensures the final chemical product is pure and meets specifications. It also protects downstream equipment like reactors and pumps from getting clogged or damaged by these unwanted solids. In this world, the purity of a chemical can determine its effectiveness. So precise filtration is not just helpful, it's absolutely necessary for creating a high-quality product. You'll also find non-sterile filtration hard at work in the food and beverage industry. Think about making apple juice. After the apples are pressed, the juice is cloudy with tiny bits of pulp and peel. Filters are used to remove these solids to create the clear, crisp juice you see in the carton. The same goes for beer and wine, where filtration removes yeast and other sediment after fermentation to clarify the final beverage. This process improves the appearance, taste, and shelf life of the product, making it more appealing to you, the consumer. It's a key step in turning raw ingredients into a finished, marketable good. Don't forget about industries like mining and metalworking. In these fields, large amounts of water are often used to cool machinery or process materials. This water can pick up a lot of grit, metal filings, and other debris. Before this water can be reused or safely discharged back into the environment, it must be filtered to remove these contaminants. This not only helps protect the environment from pollution, but also allows companies to recycle water, saving a precious resource and reducing operational costs. From the water we drink to the products we buy, non-sterile filtration is an unsung hero of our modern world. When you need to filter something, you can't just grab any old material. Choosing the right filter media, that's the stuff that does the actual filtering, is a critical decision. It's like picking the right tool for a job. You wouldn't use a hammer to turn a screw. Different materials have different properties, and the choice depends on what you're filtering, the temperature, and the chemicals involved. Common materials include polymers like polypropylene and nylon, natural fibers like cotton or cellulose, and even metals like stainless steel. Each one has its own strengths and weaknesses. Polypropylene is a very popular choice because it's like the jack of all trades in the filter world. It's strong, it doesn't react with many chemicals, what we call chemical compatibility, and it can be made into filters with a wide range of pore sizes. This makes it incredibly versatile for everything from filtering water to chemicals. Cellulose, which is basically paper, is another common option, especially for less demanding jobs. It's inexpensive and great for trapping particles, but it might not hold up as well with aggressive chemicals or high temperatures. It's all about matching the material to the specific challenge. For tougher jobs, we bring in the heavy hitters. Stainless steel mesh filters are perfect for high-temperature applications or when filtering very corrosive liquids that would eat away at plastic or paper filters. They are strong, can be cleaned and reused many times, which can save money in the long run. Another advanced material is fiberglass, which is excellent for fine filtration because its fibers create a complex path that is very good at trapping tiny particles. The key is to understand the liquid you are working with, its chemistry, its temperature, and the size of the particles you need to remove. The physical form of the filter media also matters. Some filters are made of woven fibers, like a cloth, while others are non-woven, where the fibers are bonded together randomly. This non-woven structure creates a complex maze-like path for the liquid to flow through, which is very effective at trapping particles of various sizes throughout its depth. Other filters are membranes, which are thin sheets with precisely sized holes. The science of filtration is all about understanding these materials and structures to select the perfect barrier to stop the unwanted particles in their tracks. Once you've chosen your filter material, the next big question is, how big are the holes? The pore size of a filter determines what gets through and what gets caught. This is measured in microns, which are incredibly tiny units. 1 micron is 1/1,000,000th of a meter. To give you an idea, a human hair is about 50 to 70 microns thick. Filters can have pore sizes ranging from hundreds of microns, which would catch sand, down to less than 1 micron, which can stop bacteria. Choosing the right pore size is a balancing act between how clean you need your fluid and how fast you need it to flow. Filter ratings can be described in two ways: nominal and absolute. A nominal rating is a bit of an estimate. For example, a 10-micron nominal filter will catch most particles that are 10 microns or larger, but some might still sneak through. It's like a fishing net that catches most of the big fish but lets a few get away. An absolute rating is much more precise. A 10-micron absolute filter is guaranteed to stop at least 99.9% of particles that are 10 microns or larger. It's a much stricter standard, used when it's critical that no particle above a certain size gets through. The choice between these ratings often comes down to performance versus cost. Absolute rated filters are more expensive because they are more difficult to make and test. However, they provide a higher level of assurance, which is essential for protecting very sensitive and expensive equipment. Nominal rated filters are more economical and are perfect for pre-filtration or general-purpose applications where catching almost everything is good enough. You have to ask yourself, how important is it to catch every single particle of a certain size? The answer will guide your choice. There's also a trade-off between pore size and flow rate. Imagine trying to pour water through a screen door versus a coffee filter. The water flows much faster through the screen door because the holes are bigger. It's the same with industrial filters. A filter with a smaller pore size will provide finer filtration and a cleaner product, but it will also create more resistance, causing the liquid to flow more slowly. This can slow down your whole production process. So engineers have to find the sweet spot, a pore size that is small enough to do the job, but large enough to keep things moving efficiently. Sometimes, a single filter just isn't enough to get the job done, especially when you're dealing with a liquid that's really dirty. If you try to use a very fine filter right away, it would clog up almost instantly. That's where multi-stage filtration comes in. It's a brilliant strategy where you use a series of filters, starting with a coarse one and getting progressively finer. It's like having a team of bouncers at a club. The first one stops the really big troublemakers, the next one stops the medium-sized ones, and the last one catches the small ones trying to sneak in. The first stage is often called pre-filtration or coarse filtration. Its job is to remove the big chunky stuff, the sand, grit, and large debris. This stage typically uses a filter with a large pore size, like a screen or a bag filter. Think of it as the heavy lifter of the system. By removing the biggest particles first, the pre-filter protects the more delicate and expensive filters that come after it. This makes the entire system more efficient and helps the finer filters last much longer, which saves a lot of money on replacements. It's the first line of defense. Next comes the intermediate stage. This stage uses a filter with a smaller pore size to catch the medium-sized particles that made it past the pre-filter. This might be a cartridge filter with a nominal rating, designed to capture a broad range of smaller sediments and silts. Each stage of filtration lightens the load for the next one. The liquid gets cleaner and cleaner as it moves through the system. This step-by-step approach prevents any single filter from being overwhelmed by too many particles of different sizes, ensuring a smooth and steady flow through the entire process. Finally, we have the last stage, which is the fine or polishing filtration. This is where the smallest, most difficult to catch particles are removed. This stage uses a filter with a very small pore size, often an absolute rated filter, to ensure the final liquid meets the required purity standard. By the time the liquid reaches this filter, it's already quite clean, so the polishing filter only has to deal with the tiniest of particles. This multi-stage strategy is a smart, economical, and highly effective way to tackle tough filtration challenges, ensuring a high-quality result every time. Now that we know about filters, how do we actually use them in a system? There are two main ways to set up a filtration process: dead-end filtration and cross-flow filtration. The simplest and most common type is dead-end filtration. In this setup, the entire fluid stream is forced directly through the filter. Think of it like a roadblock. all the liquid has to pass through the filter membrane, and all the particles that are too big get trapped on the surface. This is the same principle as your coffee filter or the filter in your vacuum cleaner. Dead-end filtration is great because it's simple, inexpensive to set up, and it works very well for liquids that are not too dirty. The downside is that as more and more particles get caught on the filter surface, they form a layer called a filter cake. This cake can build up and eventually clog the filter completely, stopping the flow of liquid. When that happens, you have to either clean the filter or, more commonly, throw it away and replace it. So, while it's simple, it can lead to downtime and replacement costs, especially with dirtier fluids. To solve the clogging problem, engineers came up with a clever alternative: cross-flow filtration, also known as tangential flow filtration. In this system, the fluid doesn't flow directly into the filter. Instead, it flows the surface of the filter membrane. As it flows by, some of the clean liquid is pushed through the filter pores, while the rest of the fluid, now more concentrated with particles, continues to flow along the surface. This constant sweeping motion helps to scrub the filter surface clean, preventing the filter cake from building up too quickly. Cross-flow systems are more complex and expensive to build, requiring pumps to keep the fluid moving across the filter. However, they are fantastic for filtering very dirty liquids or for processes that need to run continuously for a long time without stopping. Because they don't clog as easily, the filters last much longer, and the system can handle much higher concentrations of solids. So the choice between dead-end and cross-flow depends on the application. For simple, small-batch jobs, dead-end is often perfect. For large-scale, continuous, and challenging filtration tasks, cross-flow is the champion. Once your filtration system is up and running, the job isn't over. You have to keep an eye on it to make sure it's working properly. Operators monitor a few key things to understand the health of the system. The most important of these is the differential pressure. This is the difference in pressure between the liquid going into the filter and the liquid coming out of it. When a filter is new and clean, there's very little resistance, so the pressure difference is low. As the filter starts to clog with particles, it takes more force to push the liquid through, so the pressure on the inlet side goes up. Monitoring this differential pressure is like taking the filter's pulse. A rising pressure difference is the #1 sign that the filter is getting clogged and will need to be changed soon. Most systems have a gauge that shows this pressure, and operators know that when it reaches a certain point, it's time for a filter changeout. Changing the filter at the right time is crucial. If you wait too long, the pressure could get so high that it damages the filter, allowing a burst of trapped particles to contaminate the clean liquid downstream. Or the flow could slow to a trickle, shutting down your whole process. Another important factor to watch is the flow rate, how much liquid is passing through the system over a certain amount of time. As the filter clogs, the flow rate will naturally start to decrease. Operators monitor the flow rate to ensure the process is running at the desired speed. A sudden drop in flow rate is a clear signal that something is wrong, most likely a clogged filter. By keeping track of both pressure and flow, operators can predict when a filter needs maintenance and schedule it, preventing unexpected shutdowns and keeping production on track. Regular maintenance is key to a long and happy life for your filtration system. This includes not just changing filters, but also checking for leaks, making sure pumps are running correctly, and keeping good records of when filters were changed and what the operating pressures were. These records can help identify patterns and optimize the filtration process over time. A well-monitored and well-maintained system is reliable, efficient, and cost-effective. It's all about paying attention to the signs the system gives you and taking action before a small issue becomes a big problem. At the end of the day, running a factory or a plant is a business, and that means costs matter. Smart filtration isn't just about getting gunk out of a liquid, it's about doing it in the most economical way possible. One of the biggest ongoing costs in filtration is replacing the filters themselves. To manage this, a key strategy is to make your filters last as long as possible. As we discussed, using a multi-stage filtration system is a great way to do this. The cheaper, coarse pre-filters take the brunt of the dirty work, protecting the more expensive fine filters downstream and extending their life. Another way to save money is by choosing the right filter for the job and not over-specifying it. It can be tempting to choose a filter with the smallest possible pore size, thinking cleaner is always better. But as we learned, finer filters cost more and can lead to lower flow rates, which might require a more powerful and more energy-hungry pump to overcome the pressure. A smart operator or engineer will select a filter that meets the required quality standard but is not excessively fine for the application. This balances performance with the cost of the filter and the energy needed to run the system. In some systems, especially those with durable filters made of materials like stainless steel, cleaning and reusing filters is a great option. Instead of throwing a clogged filter away, it can be removed from the system and cleaned using a process called backwashing, where water is flushed backward through the filter to dislodge the trapped particles. While this adds a step to the process, the long-term savings from not having to constantly buy new filters can be significant. This approach is not only cost-effective, but also more environmentally friendly, as it reduces waste. Ultimately, mastering non-sterile filtration is about finding that perfect harmony between quality, efficiency, and cost. It's about understanding your process, choosing the right materials and systems, and monitoring performance carefully. By following best practices, like using multi-stage systems, optimizing pore sizes, and performing regular maintenance, industries can ensure their products are high quality and their equipment is protected. Effective filtration is a quiet but powerful force that keeps our industrial world running smoothly, reliably, and affordably. And that is some seriously cool science.